Welcome back, everybody. This is Mr. Johnson with you once again. We're in section 8.1 of our textbook. That's page 456 of our ebook. It's called The Gaseous State, and this lecture is titled Measuring Gas Pressure. It will be a bit about what atmospheric pressure is, where it comes from, the devices we use to measure atmospheric pressure, primarily the barometer, and some of the common units we use to measure pressure. There's several units that are commonly used to measure pressure, and how we can convert between those units interchangeably. I flipped my page. I'm now on 457 of the ebook, looking at this section at the top titled Measurement of Gas Pressure. And as it says here in pink, pressure is the exertion of a force on one body or another. Technically, it's the force exerted on an object divided by the area over which that force is exerted. It's force divided by area. And I'll show you what that looks like with units in a moment. Goes on to say, force is exerted on your body and on everything else by the air in the atmosphere is known as atmospheric pressure. The air that exists on Earth in our atmosphere exerts significant pressure on all surfaces at all times, referred to as atmospheric pressure. I'm going to take you to the whiteboard so we can look at the unit again for what for what pressure actually is, and talk a little bit about how gas pressure arises. So I've rewritten the formula for pressure. Pressure is equal to the force exerted on an object divided by the area over which that force is exerted. P equals F over A. Well, force, if you recall from physics, from Newton's second law, is equal to mass times acceleration. I'll use a little a for acceleration. So in the numerator, we've got m times a for force. In the denominator, we've still got area. I'll use a capital A for area. Mass, we maybe know, is measured in the SI system in kilograms. So for mass, I'm going to substitute in kilograms. This is us getting the unit for pressure. And then acceleration is meters per second squared. So we've got kilograms times meters per second squared in our numerator, divided by area, which is length times width. Length and width are both measured in meters, so in our denominator we've got meters squared. And if we simplify that by crossing through the meters in the numerator and one of the meters in the denominator, we get kilograms over meters times second squared. That's the SI unit for pressure, kilograms over meters times second squared. But that's a mouthful, and so in place of that we say Pascal. A Pascal is the SI unit for pressure, which is 1 kilogram over 1 meter times 1 second squared. A Pascal is not much pressure. We'll talk about what a Pascal is in the context of atmospheric pressure here in a moment. All right, so why does air exert pressure? Why is there atmospheric pressure? Well, hopefully you know that the molecules in a gas are in constant random motion. They're in straight line motion until they hit each other or an object, and then their direction changes. And they're moving in all directions at all times. If we average out the motion that air molecules are moving in, they're moving essentially in all directions at all times. At room temperature, air molecules are moving extremely fast. The higher the temperature of the gas, the faster on average they're moving. At room temperature, an average air molecule is moving 1,000 miles an hour. At room temperature, an average air molecule is moving at 1,000 miles an hour. When those air molecules collide against surfaces, they exert a significant force. Now, each and every air molecule, despite that it's moving at 1,000 miles an hour, does not exert much force. They're not very massive. But the collective effect of billions of air molecules colliding against the surface of an object, your skin, for example, at any one moment in time is significant. The force that air molecules exerts on the surface of objects, air pressure, is a significantly strong force. We just don't feel that. We can't feel how hard air is pushing down on us because it's pushing on us from all sides at all times, from the front of us and from the back of us. And inside of our bodies are liquids, primarily water, and other gases that are exerting an equal and outward force. So our body doesn't feel that. In fact, our skin is desensitized to feeling the effect that air pressure has on our skin. It's exerting a significant pressure, and if our pain receptors weren't desensitized to this constant pressure we experience from air pressure, we'd be in significant pain all the time. But our bodies have evolved to not register a pressure that is at or less than air pressure. Only greater than that do we register. You're going to hear me in a bit tell you that standard pressure on Earth on an average day is 14.7 pounds per square inch. What that's saying is that a force of 14.7 14.7 pounds, if it were touching your skin over a surface of 1 inch, would be exerting that pressure. 14.7 pounds over 1 square inch. That's quite a bit. If you put a 15-pound weight on just 1 square inch of your skin, you're going to feel quite a bit of pressure. The average human body is about 22 square feet of area. The surface area of our skin is about 22 square feet. That's 3,168 square inches. If we've got just over 3,000 square inches of skin and about 15 pounds of force are being exerted on each square inch, that's almost 50,000 pounds of force that are being exerted on our bodies at all times by air. And we don't feel it because our pain receptors are desensitized to it, and we've got the same pressure being exerted outwardly from the fluids and gases on the inside of our body. Crazy. The force that air pressure exerts on a surface is always perpendicular to that surface. That's what this diagram is meant to exemplify. If air molecules are moving in all directions at all times, some of them will be striking the surface of an object perpendicular to it. But the other ones are hitting at all angles. But all those angles ultimately cancel each other out because they're moving in all directions at all times, such that ultimately the net effect of air molecules striking the surface of an object is a force that is perpendicular to the surface of that object. This next section is about how a barometer works, how the device called a barometer is used to measure air pressure. While that's not a crucial component necessarily to this class, it's really interesting, and I'm about to play a 5-minute TED Ed video that explains to you how a barometer works. I encourage you to watch it. If you choose not to, you could fast forward to the end of the video and instead read this little section if you prefer. But the video, I do believe, is worth you watching. Here we go. Here's how a barometer works.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Hopefully you found it interesting to find out how a barometer was invented and how a barometer measures atmospheric pressure. From that video, we heard that one common unit for atmospheric pressure is centimeters of mercury, which could be converted to millimeters of mercury also. If you recollect, that column of mercury rose 76 centimeters high, regardless of the width of the column or the shape of the column. That is standard atmospheric pressure. On the surface of Earth, on an average weather day, not a high pressure day, not a low pressure day, but on an average day, the column of mercury is 76 centimeters high, or 760 millimeters. That is standard atmospheric pressure. Well, in another unit called atmospheres, which is based around standard atmospheric pressure, 760 millimeters of mercury is equal to 1 atmosphere, or 1.00 atmospheres. As you heard at the start of the lecture, pressure can also be measured in a unit for force over area, so it could be measured in pounds per square inch. Standard pressure in PSI, or pounds per square inch, is 14.7, which again is the same as 760 millimeters of mercury, or 1 atmosphere. Oh, and by the way, instead of calling millimeters of mercury, those can be referred to as torr, in honor of Torricelli. The idea being that torr is easier to say or write than millimeters of mercury. So torr and millimeters of mercury are interchangeable. And then also in the beginning of the lecture, you saw me derive the unit for pressure, the SI unit for pressure, which is Pascal. The SI unit for pressure is a Pascal. Well, that's so little pressure that in standard atmospheric pressure, it's 101,300 pascals, or 101.3 kilopascals. So in yellow here are the common units for pressure, and these are standard atmospheric values for all of these units that can be used interchangeably or can be used to convert from one to the other. And that's the last thing we'll do in this lecture, is just remind you through DA how we can convert from any one pressure unit to another given a pressure value. So I've written the equalities that exist between all the pressure units up top. 1 atmosphere equaling 760 millimeters of mercury, or torr, those being the same, equaling 101.3 kilopascals, all equaling 14.7 psi, or pounds per square inch. And the problem I've made up here is, what is the pressure in kilopascals of a gas that exerts a pressure of 745 millimeters of mercury? It's a one-step DA problem. So we write 745 millimeters of mercury. We know that any two things that are equal can be put into a conversion factor. I need to go from millimeters of mercury to kilopascals. So I'm going to take 760 millimeters of mercury, which I know to be equal to 101.3 kilopascals. Millimeters of mercury, of course, cancel, and that will give me 99.3 kilopascals with 3 significant figures. 760, by the way, having 3 significant figures. I should put that 0 there. The reason we do this, convert between pressure units, is because maybe it's just fun. I find it to be enjoyable. Or, like you'll find later, in certain equations, like in the ideal gas law equation, the unit for the pressure in a gas law constant called R has to agree with the unit for the pressure you plug in. So maybe you need to convert the pressure you're given from one unit to another unit so it can agree with the unit for pressure in this gas law constant. And that'll reveal itself, the relevance or significance of that to you over time, the importance for the agreement of pressure units in some of the equations we use. And while that was and is the intended end of this video, I just found one more great TED-Ed video. It's just 3 minutes long about why air is so heavy, why it exerts the pressure it does. I'd argue it's worth 3 minutes of your time. Consider hanging out and watching this. Otherwise, folks, have a great day and make the world a better place.
You may not realize it, but from the moment you got out of bed today to the point where you sat down to watch this video, you've essentially been swimming. Why? Because air is a fluid just like water. It has waves and eddies, it flows, and when you push air out of the way, it rushes around you into a wake. So why don't we notice it most of the time? We commonly think of air as empty space. But while 1 cubic centimeter of interstellar space, the volume in the tip of your pinky finger, contains roughly 1 atom, the same volume of air has about 10 quintillion molecules. If that sounds hard to wrap your head around, it happens to be about the same as the number of insects alive on the planet, all crawling, climbing, and flying over each other in an enormous, tightly packed swarm. When this swarm of molecules runs into things, it exerts a force, pressing against the boundaries of the fluid like water pressing against the glass of a bottle. This is known as air pressure. And while air is lighter than water, all those molecules still get pretty heavy, with the total air filling a typical school gym weighing about as much as an adult elephant. So when you walk into a gym, how come you're not immediately crushed by the elephant of air in the room? Well, first of all, because most of it is pressing on the floor and the walls, and the part that is pressing on you is pushed back by the pressure inside you. You see, the air, as well as the water and everything else that fills our bodies, exerts an amount of pressure equal to that of the air outside. Of course, this is no accident. It's precisely what allows us to survive in the normal atmosphere, and what makes it more difficult at high altitudes or deep water. And we normally don't feel the air pressing on us because it's generally uniform. So even though different amounts of air molecules are hitting you at different times, the swarm is so thick that all those little differences average out. What happens when air pressure isn't uniform? This means that the molecules are pushing harder in one region of air than another, driving the airflow from the higher pressure region to the lower. We feel this flow directly as wind, and the pressure systems that meteorologists are always going on about are responsible for other weather changes, from the mundane to the catastrophic. But differences in air pressure do more than just let us complain about the weather. They're the very reason we're alive. We breathe by lowering the pressure in our lungs, allowing air to rush in. So the next time you take a deep breath, think of the unfathomable number of air molecules you're commanding to move. We look up at the night sky to ponder the infinity of space. But unless you're watching this video from that deep space, there are more air molecules in and around your body than there are grains of sand in all the world's beaches and deserts, stars in the visible universe, or both of those numbers combined. The vastness of the universe is right in front of you and inside you.
Take care, folks.